valence bond theory. Already we've seen that Lewis approaches. The Lewis approach helps in the writing the structure of molecules but unable to explain the formation of chemical bond. It also does not give any reason for the difference in the bond dissociation enthalpy and bond lengths of the molecules, like hydrogen at 435.8 kilojoule per mole, the bond length is 74 picometer, and fluorine 155 kilojoule per mole and 144 picometers bond length. So although in the both cases, that's hydrogen and the fluorine, see here the both cases, the hydrogen and both cases the single covalent bond is formed by the sharing of an electron pair between the respective atom, like the hydrogen and fluorine. See, it also gives no idea about the shape of the polyatomic molecule. Similarly, in VSEPR theory also gives the geometry of a simple molecule, but theoretically it does not explain. They have some limited applications also. To overcome these limitations, the two important theories based on the quantum mechanical studies, that are valence bond theory and the molecular orbital theory. Simply we can tell MOT, VBT and MOT. The valence bond theories are introduced by the Hitler and London, the chemist, and developed by that is further on developing the Paulings and other scientists. Here, the valence bond theory based on the knowledge of the atomic orbitals, the electronic configuration of the element. So the overlap criteria of the atomic orbital, the hybridization of atomic orbital, and the principles of variation and the superposition. Right? That valence bond theory has been discussed in terms of qualitative and the non-mathematical treatment only here. Okay, because the valence bond theory is large studies. Here we are going to discuss only this mathematical treatment and the non-mathematical treatment only. Qualitative and the non-mathematical treatment only. Now consider the formation of the hydrogen molecule, which is the simplest of all molecules. Okay, consider the two hydrogen atoms like A and B. The hydrogen atom of A and B. Here the two hydrogen atoms are approaching A and B, that is each other, having the nuclei, that is Na and the Nb. Okay, that is the Na and Nb and electrons present in them are usually represented by Aa and Eb. Okay, when the two atoms are at large distance from each other, there is no interaction between them. So as the two atoms approach to each other, the new and attractive and the repulsive forces begin to operate. So first the attractive forces arise between, that is, first look at the attractive forces, that one atom, nucleus of one atom and its own electron, that is Na, simply we can the Na minus Ea and Nb minus Eb. Okay, this is nucleus of one atom and its own electron. Okay, then second is the nucleus of one atom and the electron of other atom, that is Na minus Eb, similarly Nb minus Ea, that is other atom, electron of other atom. This is for attractive force. For example, repulsive force arises between electrons of two atoms like Ea minus Eb, then nuclei of two atoms Na minus Nb. Okay, see, the attractive forces tend to bring the two atoms are close to each other, Okay, look this. The attractive force tend to bring the two atoms of each other, and whereas the repulsive force, this is the repulsive force, tend to push them apart. Okay, this is like this. Okay, and here also plus sign. This is attractive force and this repulsive force. Here, experimentally it has been found that the magnitude of new attractive force is more than the new repulsive force. As a result, two atoms approach each other, and the potential energy decreases. Okay. Ultimately, a stage is reached when the net force of attraction balances the force of the repulsion, and the system acquires the minimum energy. Okay. At this stage, the two hydrogen atoms are said to be the bonded together to form a stable molecule having the bond length. Like this is the bond length having the 74 picometer. Since the energy get released when the bond is formed between the two hydrogen atom, and the hydrogen molecule is more stable than the isolated hydrogen atom. So this is called bond enthalpy. Then, which is corresponding to this the corresponding to the minimum in the curve. See, look this, the corresponding minimum in the curve, that is conversely this is 435.8 kilojoule per mole of energy is required to dissociate of 1 mole of the hydrogen molecule. Okay, this is the potential energy curve for the formation of the hydrogen molecule as a function of the internuclear distance of the hydrogen atom, that is H atom. The minimum in the curve correspond to the most stable of hydrogen. Okay, this is bond energy, this is bond length, and the distance of the separate atoms, that is hydrogen now overlapping here. Okay, that's mean joined here. This is energy versus the new internuclear distances. Okay. Then the orbital overlap concept. The orbital overlap concept is the formation of hydrogen molecule. There is the minimum energy state when two hydrogen atoms are so near that the atomic orbitals undergo the partial interpenetration. That is interpenetration. Okay. This partial merging of the atoms of orbitals is called overlapping of the atomic orbital, which result in the pairing of electron. So the extent overlap decides the strength of the covalent bond. Usually, the greater the overlap, the stronger the bond and formed between the two atoms. Okay. Therefore, according to the orbital overlap concept, the formation of covalent bond between two atoms results by pairing of electron present in the valence shell having the opposite spin. Directional properties of bond, that is already we have seen the covalent bond is formed by overlapping of atomic orbital. So the molecules of hydrogen is formed due to the overlapping of the 1s orbital. 1s orbitals of the two hydrogen atom. So in case of the polyatomic molecules like methane, okay, ammonia, water, like this. So the geometry of the molecule is also important in addition to the bond formation. For example, why is it so that the methane molecule has the tetrahedral shape, and the HCH bond angles is 109.5 degree. Why this reason? And why the shape of the ammonia molecule is pyramidal? Okay. Here the valence bond theory explain the shape, the formation of the directional properties of the bond of polyatomic molecules like methane, ammonia, water molecule, like this in the terms of the overlap and the hybridization of the atomic orbital. Okay, this valence bond theory helps to predict the shape of the molecule. Then first, the overlapping of the atomic orbital. Okay. See, overlapping of the atomic orbital. This is the overlapping of the atomic orbital when orbitals of two atoms come close to form bond. Their overlap may be positive, negative or 0. So this is positive overlap and this is negative overlap. Or in phase overlap. This is out of phase overlap. This is in phase overlap. This is out phase overlap. That means these things. Okay. Here, the first this is the positive, negative or 0 depending upon the sign that is phase and the direction of the orientation of the amplitude of the orbital wave function in space. Look at this diagram. The positive and the negative sign on boundary surface diagram. Look at this. This is the boundary surface diagram. That is of orbital wave function and not related to charge. Okay. The orbital forming bond should have same sign and the orientation in space. So this is called the positive overlap, like this. This is the positive overlap. Okay. The various overlaps of S and P orbitals are here. That is, this is S and P orbital. This is PP orbital, like this. Okay. Then this criteria of overlap as the main factor for the formation of covalent bonds applies uniformly to the homonuclear or the heteronuclear diatomic molecules and the polyatomic molecules. We know that the shape of methane, ammonia and water, that's the methane having tetrahedral, ammonia having pyramidal and water having bent shape. Okay. It would be therefore the interesting to use the VB theory to find out of these geometrical shape can be explained in the terms of the orbital overlaps. Okay. Now consider the methane molecule. The electronic configuration of the carbon is the ground state is what? That is simply we can write it here, that is helium 2s2 2p2. This is which is in the excited state. That is in excited state we can write it like this, that is helium. This is in ground state. Okay. When excited state 2s2, that 2px1 and 2py1. Okay. So here then the 2p, sorry, this is 2s1 and 2p is at 1. Okay. So this is for ground state and this is for the excited state. So the energy required to this excitation is compensated by these by the release of energy due to the overlap between the orbitals of the carbon and the hydrogen. Okay. So this is for methane molecule. Okay. The 4 atomic orbitals of carbon, each with the unpaired electrons can overlap. This is okay. Unpaired electron can overlap with the 1s orbitals of the 4 hydrogen atoms which are strongly singly occupied. So this will result the formation of the CH bond. So it will however be observed that while there are 3 p orbitals of carbon at 90 degree, 3 p orbitals of carbon at 90 degree to one another, the HCH angle for this will be 90 degree. Okay. So that the 3 CH bond will be oriented at 90 degree to one another. So the 2s orbitals of carbon and the 1s orbitals of hydrogens are spherically symmetrical and they can overlap in any direction. So therefore the direction of the 4th CH bond, that 3 is this and 4th CH bond can be cannot be ascertained. So this description does not fit in the tetrahedral HCH molecule. Tetrahedral, so that is angle is 109.5 degree. That is, clearly it follows that simple atomic orbital overlap does not account for the directional characteristics of bond in the methane molecule. So using the similar procedure, the arguments, that is, it can be seen that the case of ammonia and the water molecule also. Here the NH, that is HNH or HOH angle should be 90 degree. This is and the disagreement with the actual bond angles of 107 degree and the 104.5 degree for water molecule. Okay, 107 for ammonia molecule. So this is the positive overlap and the negative overlap of the thing. So this is positive overlap, that is the in phase overlap. Here the s and p orbital overlap, this overlapping like this, then the overlapping like this. This is zero overlapping. Similarly, in the case of the negative overlap, like this, positive and negative, then positive here, the so that the positive and the negative overlap, the s and p orbital. Similarly, this is for zero overlap. Okay. Types of overlapping and the nature of covalent bond. The covalent bond may be classified into two types depending upon the types of the overlapping, that is sigma bond and pi bond. Here first the sigma bond. This is the type of covalent bond formed by the end to end, that is head on overlapping, and the bonding of orbitals along the internuclear axis. So this is called head on overlapping or the axial overlap. This can be, that is formed by any one of the following types of the combination of the atomic orbital, like SS overlapping, SP overlapping and PP overlapping. First we will see the SS overlapping. There is, in this case, there is the overlap of two half-filled s orbital along the internuclear axis like this. So this is one s orbital and this also s orbital. Okay, gives this overlap like this. So this is the SS overlapping. And the SP overlapping. This overlap occurs between the half-filled s orbitals of one atom and half-filled p orbitals of the other atom. Like this, see, s orbital and this is the p orbital. The overlap like this. Okay, this is SP overlapping. Then the PP overlapping, the type of overlapping takes place between the half-filled p orbitals of two approaching them like this. So these this one p orbital and this one p orbital, this approaching like this. The overlapping like this. So this is the PP overlapping. Okay. Then p pi, that is p pi bond overlapping. Not p, pi bond overlapping. This is the sigma bond and the pi bond overlapping. The pi bond overlapping, the formation of pi bond, the atomic orbitals overlap in such a way that their axes of remain parallel to each other and perpendicular to the internuclear axis, so that the orbitals formed due to the sideways overlapping consist of a two saucer type charged clouds above and the below and the participating atom, like this. See, suppose the p orbital. This one p orbital and this another p orbital, two overlapping like this. So this is the pi bond formation. Okay, or you can write it like this. This one overlapping. This is this is pi bond overlapping. This is the sigma bond overlapping, and this is the pi bond overlapping. This means the head-on overlapping, two head like this. So head-on overlapping or end-to-end overlapping. This is sideways overlapping or the lateral overlapping. Then the strength of the sigma and pi bonds are basically strength of the bond depends upon the extents of overlapping. So in case of the sigma bond, the overlapping of orbital takes place into the large extent, so that the stronger the stronger the bond is sigma, okay, compared to the pi bond. Okay, here the pi bond is the extent overlap occurs in smaller extent. That's why they are weaker compared to sigma bond. Okay. Here it is important to note that there is formation of multiple bond between the two atoms of molecules. Pi bond is formed addition to the sigma bond. Then next is a hybridization. We will discuss in next class.